Beneath the topsoil of these Bedfordshire fields lies grey glacial till left behind by an ice sheet that retreated thousands of years ago. But beneath this are 60 to 70 metres of a much older sandstone, the lower greensand, deposited over 100 million years ago during the lower Cretaceous. The lower greensand occurs in many parts of England and is exposed in quarries where the sand is extracted to supply the construction industries. The quarry faces are full of sedimentary structures, formed as the sand was deposited. Structures like these, and the textures and mineralogy of the sandstone, provide a record from which it's possible to deduce a great deal about the history of transportation and deposition of the sediments.
It's fascinating what you can learn from just a few meters of sediments like these. But of course, piecing together all the clues that will let us unravel the history requires a lot of careful work, including both the collection of field data from many sites and the more detailed investigation of samples in the laboratory. I'm going to concentrate on just this one exposure to give you some idea of how we go about collecting data, and then show you how we can interpret these data to make some tentative suggestions as to the history of these sediments. Of course, a fully comprehensive survey would involve the collection of data from many sites, noting carefully vertical and lateral variations in the sequence of sediments. To do this, I need a simple but effective method of making the comparison and of recording my field data. This is done using a log sheet. Now, this is a log sheet which I prepared in advance before coming out into the field. Along the side here is a scale in meters which records the height, in this case, above the base of the exposure. Features like thickness, the unit or bed, the lithology, grain size, sedimentary structures, and colour are recorded in separate columns, and there's a spare column at the end for other remarks I might wish to make. This is a log sheet I've just completed for this exposure. My first step was to decide upon the lithology. Now, I'm fairly happy to call all this a poorly consolidated sandstone. It's mostly composed of sand-sized quartz grains. And this pattern on the log is a conventional symbol of dots to represent both sands and sandstones. But there is the occasional gravelly bed, like this. And I've shown these on the log here and further up here. These are reflected in the grain size. They're coarser. And you can see that the line down the right-hand side of this column represents a graph of sediment grain size against the height above the base of the exposure. Now, this provides us with an easy format for recognizing grain size variation as we move up the sequence. We go from coarse-grained here through to finer-grained sediments and then back to a coarser layer at the top. I've not commented on this section here because it's covered with loose sand. But grain size is important in sandstones because it's related both to the way in which the sand is transported and the way in which it's deposited. Structures are important too because they tell us something about the way deposition occurs. And you will see that I've drawn the layering inclined rather than normally horizontally. In other words, I've indicated that these sands are cross-bedded. To see how this is done, let's look at this piece at the top of the sequence. There's a clear distinction here between these white sands, which are overlain by these brown, much coarser, gravelly sands. The sands were deposited originally along a plane inclined down to the right, like this. And these sands were deposited originally along a plane inclined down to the left, like this. Now, we'd normally expect sediments to be deposited horizontally, and this is why we refer to these as being cross-bedded. Let's take a closer look at these white sands. I can see that they're actually coarse-grained. Some of the grains are quite well rounded. There's a wide variation in grain size present. And in fact, this layering is picked out by the variation in grain size. I've made a note of all these sorts of observations on my log sheet here. Well, this is one example of cross-bedding. Further down the sequence, here, we have a different pattern, known as herringbone cross-bedding. The layering is a little less easy to see, but you should be able to distinguish that the lower set of beds are inclined down to the left. The upper set are inclined down to the right. And the junction between them is quite horizontal. That is what gives the herringbone effect. Let's take a closer look at the sand grains themselves. This is a medium-grained sand. The grains are still well-rounded, but there's less variation in grain size, so it's better sorted. Once I'd collected field data from this locality, my next step was to extend my field observations by examining the samples under a microscope. To begin with, we'll examine two samples. The first came from the white sand at 7.5 metres, near the top of the section. As we saw in the field, it's quite coarse-grained. Most grains are between 0.25 and 1 millimetre across, and there are a few larger gravel-sized fragments. Grain shape is classified on a visual scale from angular to well-rounded. Here, the larger grains are sub-rounded, and the smaller subangular. The grains consist almost entirely of one mineral, glassy quartz. The second sample came from 4 metres above the base of the section. It's finer grained and a little better sorted. The grains have a brownish colour caused by a surface coating of iron oxide. But the important thing to see is that the grain shapes are similar to the previous sample, and again, they're mostly quartz. So overall, the sands are texturally quite mature, as they're moderately well sorted with some sub-rounded grains. And as they consist mainly of quartz, one of the minerals that's most resistant to weathering, I'd describe them as mineralogically mature as well. The textural and mineralogical maturity of quartz sands like these reflect the intensity and duration of the weathering and transport processes that have affected the grains prior to their final deposition. To appreciate these effects, we need to go back perhaps millions of years to the initial derivation of the grains from crystalline, quartz-bearing rock.
This granite on Bodmin Moor looks hard and solid enough, but all the time it's slowly disintegrating. Rainwater seeps into well-developed joints like these, and when it freezes, unlike most other substances, it expands, and this prizes the rock apart. Rainwater also attacks the granite chemically. The grain boundaries are attacked first, so that the granite slowly rots and crumples, releasing small crystalline aggregates and individual crystals of quartz, feldspar and mica.
The important thing to notice is that the freshly weathered fragments are coarse, very angular and totally unsorted. So this new formed sediment is texturally very immature. The mineral proportions of quartz, feldspar and mica are the same as in the parent granite, so none of the less resistant minerals, such as the feldspar and mica, have been chemically decomposed yet. So the newly formed sediment is also mineralogically immature. Clearly, this gravelly sediment bears little resemblance to the lower green sand. So if the quartz grains in the lower green sand were derived in the first place from a weathered crystalline rock, they've undergone a lot of changes since.
The changes begin when the weathered debris enters the phase of transport and is gradually moved away from the site of weathering. After heavy rainfall, water runoff collects and streams begin to form. These grow in size until they're able to transport sand and gravel. Here, the processes that lead to textural maturity are already apparent. A spadeful of mixed sediment lowered into the stream shows that the flowing water is quite selective in what it transports. While the sand and even quite coarse sediment is washed away, the larger pebbles are left behind. So the flowing water is beginning to sort the sediment into different size fractions. All but the finest sediments are transported as bed load, rolling and bouncing or saltating along the river bed. These constant collisions abrade the grains, causing another aspect of textural maturity, grain rounding. This affects the largest fragments most rapidly. Even though these pebbles have been transported only a few kilometers down the River Foy, they're already well-rounded. By contrast, the finer gravels still quite angular. This is because the impacts of smaller grains are more effectively cushioned by the water. The further the river carries the sediment, the more opportunity there is for the flowing water to sort and abrade the sediment. This also affects the proportions of the minerals in the sediment. This coarse sediment's made up of quartz and feldspar and contains little mica. Because of their shape, the shiny flakes of mica have been carried away in suspension and deposited along with the finer sediment where there's very little water movement to disturb them. But rivers don't just transport sediment, they use it to erode the bedrock over which they flow. These falls are formed where the river flows from the harder granite onto softer slates. The slates have been eroded more rapidly, and now the river is cutting back into the granite. The sediment is tumbled and pounded on the bedrock like pebbles in a ball mill. All this work is bound to have some effect on the sediments that reach the lower part of the Foy Valley. At Loswithiel, we're only 10 kilometers from the sea. Here, the Foy is tidal. As the incoming tide affects this part of the river, water floods over the edge of the main channel. The coarser sediment is dropped near the main river channel where the river flow is fast. But the finer material is deposited at the edge where the slack water occurs only at high tide, causing the formation of sandbanks.
This is some of the coarser sediment. It's still quite poorly sorted, but some of the larger grains are more rounded, so it has begun to mature texturally. There are now some of the slate fragments mixed in with the granitic material. They've been rounded more rapidly than the quartz grains because they're softer, so the sharp corners and edges are more easily smoothed. Feldspars don't tend to become very rounded as they cleave too easily on impact. There's less feldspar and mica present in the coarse sediment, so it's mineralogically more mature too. So it's changed quite a lot from the original freshly weathered granite debris. But it's still very different to the green sand. The sediment from the sandbank shows how most of the shiny mica has been sorted out and deposited with the finer quartz, feldspar and slate fragments.
Eventually, the sediment that survives transport down the river reaches the sea. Here it's mixed with sediment derived from the erosion of the local cliffs and carried along the coast by waves and currents to be deposited as beach sands in the bays and coves. Here, the sands are in almost constant motion as the breaking waves push them up the beach and the backwash draws them down again. By this incessant movement, the sand is moved and abraded in just 1 week, as much as in the months or years that it took on its journey from Bodmin Moor to the sea. The incessant motion also leads to rapid sorting. Coarse sand is deposited near the headlands, where the wave action is strongest, while fine sand is deposited on the beach in the center of the bay, where the wave action is gentlest. Over a period of a few years, these sands may have traveled the equivalent of several thousand kilometers. In this distance, many more changes take place.
Even this coarse beach sand is well sorted. The grains have developed much smoother outlines, so texturally it's much more mature. The grains are mainly quartz now, mixed with a few fragments of slate and quartzite derived from the cliffs, so mineralogically it's much more mature too. Although the beach sand is coarser grained than the green sand, overall its textural and mineralogical characteristics are quite similar. So what can we tell about the lower green sand from all this? To achieve this maturity, it must have spent a considerable period of time in transport, but this need not necessarily have been in the sea. Extended transport by river or repeated cycles of weathering, erosion and transport would have had the same effect. To find out more about how transport and deposition took place, we must turn to the structures in the lower green sand. Cross-bedding is a sign that the sands were not deposited in flat, even layers, but the sediment surface was disrupted by a series of bed forms. Ripples formed by waves moving over a beach are a common bed form. To find out whether the cross-bedding in the lower green sand could have been formed by waves, we need to find out exactly how sand is moved and deposited by waves.
This flume tank at Cambridge University has been set up to demonstrate the action of waves as they pass over a layer of sediment. As the wave crest passes, sediment is lifted from one side of the ripple and deposited on the other. As the wave trough passes, the process is reversed. This backwards and forwards movement gives the ripple a near symmetrical form. When there's a constant supply of fresh sediment, there is net deposition on both sides of the ripple, leading to strata inclined alternately to the left and right, forming a chevron pattern.
None of the cross-stratification I observed in the lower green sand corresponds to the chevron cross-stratification produced by waves. So it's unlikely that these sediments were influenced by wave action. Flowing water also produces bed forms, but in this case the sediment movement will be predominantly in one direction. So we also need to examine stratification formed by unidirectional current flow.
At low current velocities, there's no sediment movement. But as the current increases, the friction between the surface grains and the underlying sediment is overcome, and grains begin to move slowly along the flume tank. The rotation of the current meter screw gives an indication of the relative current velocities. At higher velocities, the surface of the sediment is disturbed as current ripples start to form. These are asymmetric in cross-section, and the overall movement of sediment is in the direction of current flow. Bed load moves up the shallow Stoss slope over the crest, then avalanches down the steeper lee slope. Sediment caught up in eddies in the ripple troughs is swept back up the lee slope. So the Stoss slope is a region of active erosion and the lee slope a site of deposition. This causes the ripple form to migrate down current. When ripples first form, their crests are linear. But as the current velocity increases, the straight crests break up into shorter curved sections, known as lingoid ripples. As the current velocity increases, the size and amplitude of the bed forms increase. Eventually, this should lead to the formation of sand waves and subaqueous dunes. But the flume tank isn't large enough for these to develop. Instead, the ripple forms are washed out as the conditions pass straight from lower to upper flow regime conditions. Once again, the surface of the sediment is smooth, but now a thick carpet of sand moves across the surface, and any sediment deposited will form horizontal layers or planar beds. Similar patterns of cross-stratification are produced by both current-formed ripples and subaqueous dunes, although they differ in size. By adding dyed sand, it's possible to pick out the stratification formed as ripples migrate down current. To speed things up, only stages of the movement will be shown. The dyed sand is only preserved on the lee slope, where it's buried by further avalanches as the ripple migrates. So the cross-stratification picked out by the dyed sand records the position of the lee slope, and so it is always inclined downstream in the direction of current flow. Here the ripple form has been outlined so that you can see what happens as it continues to migrate. The first set of cross strata are partly planed off by erosion, but a second set of cross strata are formed on top, preserving the remains of the first set. Thus, sets of cross-stratified ripple deposits can accumulate in which the cross strata all dip in the same direction, indicating the direction of current flow. While variations in the color of the sediments often pick out cross-stratification in natural deposits, so can variations in the grain size of the sediment. But larger grains tend to collect towards the bottom of the lee slope, so cross sets tend to be more coarsely grained towards their base.
Patterns similar to these unidirectional current-formed sets of cross strata are seen in the cross-bedding of the lower greensands. So it's very tempting to suggest that the lower greensands were deposited from a fast-flowing unidirectional current. But there's one more clue to bear in mind first. This herringbone cross-bedding indicates that here the current reversed its direction completely, not very likely in a river channel. But there are water currents which do reverse direction, tidal currents. If deposition and preservation occur on both the incoming flood tide and the outgoing ebb tide, which is rare, then herringbone cross-bedding develops. So it's possible that the greensands were deposited in a fairly shallow tidal sea, but below the influence of wave action. This idea is consistent with the structural and textural evidence I collected from just the one location, but this is not the end of the investigation, it's only the beginning. The next stage would involve many months of work collecting data from other parts of England. Only then can I hope to confirm this idea.